Right, ladies and gentlemen, good morning. We are a very decimal lecture today. It's lecture 20, October 10. That happens to be 10/10. And we're starting at 10 minutes after 10. And it's just something's going on with our stars are colliding. Okay, so announcements. We've got a homework due Wednesday, Thursday. We will post solutions Thursday evening. The midterm is here during the lecture hour. Please arrive promptly. All this dribbling in hopefully won't happen next Friday. Follow seating instructions. The seating instructions are very simple. Start sitting from the front and coming in both sides, walk to the center of the row. Do not leave gaps. We will start handing out exams from the front. As soon as a row is finished, we will complete, we will hand out exams for that row. If somebody sits at the edge of the row and therefore leaving gaps and forcing people to climb over them, then that row will get its exams at the end. That's unfortunate. We don't want this. The simplest thing to do is to come and forget where you normally sit. Right? Just come from the front, fill in, just come into the center. And then we hand out the exams. The exams have a cover page. Did you all receive the multiple emails that I sent? Right? So you should have received by now the cover page of the exam, the cheat sheet that we're handing out, which is two-sided, and also last fall's midterm. It isn't exactly last fall's midterm because their sequence was a little different, so I adjusted some of the problems to make it. You've got all that, yes? All right, so we'll hand out the exam. It'll have the cover page on top of it. Nobody will start until I say go. Except that if there are some rows which we're having trouble seating, other people might go if for some reason we have people with difficulty understanding instructions. Just when you come in, find the row closest to this side that has an empty space and go all the way as far inside as you can go, and that'll do it. So I've planned the exam for 45 minutes because it does take, with a class as big as this, it takes a while to get going. 45 minutes, 8 questions. You know this, right? From the cover sheet that I sent around. So it's roughly 5 to 6 minutes a question. However, some questions will take 1 minute or 2 minutes, and then you have more time left over for other questions. So not all questions will take the same amount of time. I've tried to make the exam easy for you to write on, so there's plenty of space. Each question there are 8 pages. Right? Each question is on 1 page. And there is a block of space for answering the question and parts. Sometimes the question has 2 parts. Now, if a question has just the one question, no parts, then you have the entire page to write in. That doesn't mean I'm expecting you to write a 1-page essay. I'm expecting you to write 2 good sentences. You don't have time to write a 1-page essay. Right? So just because there's space, don't feel you have to fill it. Often we ask you for 1 line of code, and that line, when you write, it might not fit in 1 line. It may come back down. That's fine. I just need to be able to type it into Python as 1 line and have it execute. All okay? I don't think there will be, if you look at your homeworks and the midterm that went out last fall, they did extremely well on that, by the way. I don't think you will be surprised by the nature or the tone of any question. It's just, you have to think about each one. Review. Textbook, homeworks, labs, and projects. Please understand, each question is rather short. This is what I call the bite-sized exam. And so I can't give you something that's a sustained calculation from beginning to end, but when you look at simulations or you look at some calculation that we've done, understand that any part of it is fair game. Right? So take the bits separately. And even if you can't recreate the whole thing from beginning to end, you should understand the individual bits. Okay, so my office hours, I have to shift my office hours. There's something, normally on Tuesdays I have office hours in the morning. Tomorrow I have to have them in the afternoon. There's something I have to go to in the morning. So tomorrow, instead of 10 to 11:30, I'm available 1 to 2:30. I'll post on Piazza. I will be available at some point on Wednesday and at some point on Thursday as well. I just don't know what time yet. I'll post on Piazza when I know. And the GSIs and tutors are, of course, available. Okay, so I will, material for the exam, everything up through today. Now, I'm not going to teach anything new today. I am going to do a significant example using what we've done in the last week. And I'm going to finish up some stuff that we were doing on Friday that went a little fast. Questions? What are you going to bring with you? Pencil, eraser. Yep. So I would really appreciate if you use pencil and eraser rather than pen, because if you have to change an answer in the pen, then you go outside that box, and then Gradescope has problems. And so please, revert to middle school and use pencil and eraser. All right. If you need space to work something out, the back of every page is blank. So you can turn it over and write as much as you want, but you don't have that much time. So thinking about the question may be more helpful than writing a bunch of stuff. But the people's styles are very different. Okay, if no questions, we'll get going. So where we were last time, we were talking about errors in a type of error when we make decisions using tests of hypotheses, and the key was how we make the decision at the end. The decision is made based on a p-value. What is the p-value? It is a probability. It is computed under one of the two hypotheses, the null hypothesis. And the key was that it is the chance of getting what was observed, the statistic that was observed in the sample, or something even further in the direction of the alternative. And that is what we spent some time on last time. And we recognized that a test conclusion can be wrong. There are two kinds of error. The test says alternative, but the null is true. And the test says null and the alternative is true. We'll focus on this one. The null is true, but the test says alternative. The reason we focus on this one is we can actually talk about chances of that happening. If the alternative is true, frequently there aren't chances involved. Remember that our very first test of hypotheses that we did, the jury looks like a random sample from a population was the null. The alternative was the jury does not look like a random sample, right? It wasn't drawn at random. Well, if it wasn't drawn at random, then there are no chances involved. So that is a more subtle error to deal with. We will focus on the first kind, over which we have some control. And what we had noted right at the end of Friday's lecture was that if you have a cutoff, then that cutoff is the chance you're going to get an answer wrong. So if you use, and we were using 6% as a cutoff that day. If your cutoff is 6% and the null hypothesis happens to be true, you can still conclude alternative, and that will happen about 6% of the time. So do you understand why people want a low cutoff? Yes, medical studies use a 1% cutoff, because they're trying to control for this error probability. If they use a 1% cutoff, usually what they're testing for is this treatment has no effect versus this treatment has an effect. Right? They really don't want to end up concluding it has an effect when it doesn't, right? Because you can cause untold grief that way. So they have a very conservative cutoff usually of 1%. And what that's saying is that in the long run, if the treatment is just water and does absolutely nothing, then the chance that they will wrongly conclude that it does something is only about 1%. So you have some control over this kind of error by your cutoff. It's a fact almost that if you try to reduce one kind of error, you end up increasing the other kind. You've seen my life is tough slides before. It's something that we have to face. But for now, it is important to understand that that cutoff is an error probability. Now, I'm talking about errors. So if you have a cutoff of 6%, there's a 6% chance you'll get the answer wrong if the null hypothesis is true. What's the chance that you get the answer right? 94% beats tossing a coin. So if you use a 1% cutoff, yes, you have a 1% chance of being wrong if the null hypothesis is true, but you have a 99% chance of being right. So these methods are good. Okay, so what I'd like to do is just remind you where we were at the end of last lecture. We were testing for the fairness of a coin. And what I'd like to do today is I would like to be very clear about, null hypothesis, alternative hypothesis, which is which, and where precisely does each hypothesis come into your calculation. Okay? Right, ladies and gentlemen, the null hypothesis. Okay, so somebody says the coin is fair, right? You have two options, fair, not fair. Those are your two options that I'm giving you. How do you decide which one becomes the null? I'm sorry? Whichever one is not just whichever one's random, but whichever one is a completely specified way of randomness. So this says random and drawn from heads, tails. Not just random and drawn from any old coin which may be biased and I don't know. Okay. So it's a completely specified chance model because after all, you have to do a simulation under that model. You better know what the model is. So your null hypothesis is the coin is fair, so draws at random with replacement from heads, tails. And the alternative is that the coin is not fair, right? I'm just testing fairness, and I haven't tossed anything yet. So I'm not saying that it's biased in one direction or another. I'm just saying that it's not fair. Okay. So that's now what we do is we will set up our simulation of the statistic, which we did last time, and see where these two hypotheses enter the picture. Okay, so I'm going to have to draw at random with replacement from heads, tails, so it's natural to set up this array. We had decided that we were going to use 400 tosses of a coin, so I'm setting up 400 tosses of a coin. Fine. And then we will run. Okay. Repetitions, 10,000, my choice. You can have 5,000, 17,000, whatever you want. Okay. You start in any simulation by a blank array in which you are going to collect your data. Okay. Where does this come from? I'm just saying heads. Yep. There was a decision made there. What was the decision about? It is about some aspect of your test. There's a decision has been made. Subliminally, we haven't said it. The test statistic has been chosen. And the test statistic that we have chosen is the number of heads in 400 tosses. All right, so before you start your simulation, you have to know what you're going to simulate. And the choice of the statistic matters. Yes? Not clear to me entirely that that is a good statistic by itself there. How do you decide between one statistic and another? You have to look at the null versus the alternative. This thing has to be able to help you decide between the two. Fair versus not fair. Yep. 400 tosses of a coin. Fair, the number of heads should be around 200. Yep. And unfair, it should be either quite low or quite high compared to 200. If you have the number of heads as your statistic, then you are going to have this issue of what you're going to do with your p-value. Left side, right side, what? Right? So can you adjust this number of heads? It's on the board. Can you adjust this number of heads so that it's very clear what you have to do, which tail you have to look at? You're looking at how far this thing is from 200. You agree? What measures how far? Distance, no sign. So you can collect the number of heads by all means. Yep. But in the end, you are going to do heads minus 200 absolute value. We did this last time, and please note, The alternative comes in your choice of statistic. You have to be able to tell the null from the alternative easily. So it comes in there. All right, so we have a statistic. We have a number of repetitions. I already called this num tosses. I'm going to call this num tosses. Okay, so we're going to repeat, and we are going to collect the number of heads. Okay, somewhere in these two lines, the null hypothesis has come in. Where in those two lines has the null hypothesis come in? Two lines, not too much to look. What's happening in the first line? You are selecting at random. You are selecting at random from what? From that. Yes? What kind of coin is that? It's a fair coin. 50% chance of getting heads every time. Yep? What you simulate from, what you draw from, is the model of the null hypothesis. That's where the null hypothesis comes in. So you have to be very clear about what your null hypothesis is so that you can sample at random from the right thing. Okay, once you have done that, then it's a matter of collecting. So far, it's a matter of collecting your results. We have an array that has our collected statistics, and then we show it in, we put it in a table, and then, okay, let me run this thing. And then, okay. So I want you to notice something. We haven't actually done our experiment yet. Nobody has tossed any coins. What we have done is a thought experiment. We have said, had a fair coin been tossed 400 times, then we would have got varying values of the statistic depending on how the tosses came out, and those would have been distributed according to this. So you can do the bulk of the work in a test without actually ever having run your experiment, just using a computer to generate under the null hypothesis. Okay, so now your decision is where do you decide the coin is fair or not if you actually now run your experiment. Yes? My test statistic is this quantity. It's not the heads. This is the test statistic. Number of heads minus 200. Absolute value. Right? So the heads is a natural first thing to start with. Right? And it's easy to code. But when you look at the alternative, it's not saying bias towards heads. It's not saying bias towards tail. It's just saying biased. That means there's a two-way distance without regard to sign. So that has to come into the statistic somehow. Those of you who have done any classical statistics will know that there's a lot of discussion about it. Is a one-tail test, is a two-tail test. It all has to do with people being afraid to use absolute values. Right? For us, it's no problem. We just have to decide whether it suits the alternative or not. So in this case, it does. And now you know that if we got 200 heads, our statistic would be 0. If we got 205 heads, we'd be here. Yep. And so if we got a statistic anywhere here, we would be saying, I can't say it's not fair. Somewhere along here, we start to worry. Right? About here, most of us will be quite worried about whether the coin is fair. So starting here, not worried, fair, and then somewhere here, we start getting worried, are we going to conclude unfair? Right? Where that somewhere is depends on what? Thank you. Our subjective opinion about what's too far. That is what it depends on. That is exactly what it depends on. How are these things codified? Your subjective, how would you measure that? Terrific. So it's however I would deem was a cutoff point. Excellent. So it's up to you to deem what is a right cutoff point, right? And on Friday, we had said our cutoff point is going to be 6%, right? Now, before I get deep into the weeds of what happens with the 6%, what I'd like you to notice that you have subliminally said we have to look at the right-hand tail. It's the right-hand tail that's going to bother us. Yep. And because low values of the statistic look like the null and high values look like the what? The alternative, once again, the alternative comes in there. That you are looking at the right-hand side. Under the alternative, you expect the statistic to be large. Right? So you're going to look at right-hand tails. It's not just small tails, but tails in the direction of the alternative. Okay, so if you were using a 6, did I have 6? Yes. So I had a little picture drawing thing which I implore you not to worry about. I just showed where the 6% cutoff is. It's right there. So this is where if you use the 6% cutoff, that's where you will start saying, I don't think so. I think it's unfair. And if instead you were using a 2% cutoff, what would happen to this red segment? Oh, I got both answers instantly. It would be bigger, it would be smaller. Which? You would worry. Would you be worried here if you were using a 2% cutoff? That's the 6% mark. You'd have to go out until you hit 2%, yes? Should we run it? You now start worrying over here. Right? Okay, so I'll go back to 6. Okay, so you can see that for values of the statistic here onwards, you will say alternative, but you can also see that there are values of the statistic there. If you toss a fair coin, such values do appear, and they appear what percent of the time? 6% of the time. That's what that cutoff means. You are willing to make an error 6% of the time. That's what you've decided. Does this feel like a review of something we had on Friday? Yes? Okay, it's quite important to get this down, what that cutoff means. All right, now, there are people in the room. Yes? Does the cutoff depend on the test statistic at all? No, the cutoff is a cutoff for a probability. So the cutoff is a number between 0% and 100%. Yes? Whatever the statistic is, it doesn't matter whether it's a total variation distance or a number of purple flowers or anything. In the end, you're going to think about, okay, what probability is low enough that I start to worry? Yep? So it's just a question of what chance do I think is small? Right? And as you heard a little while ago, it's up to you. And what you think is small might really depend on the situation at hand. Right? I mean, if I think somebody has chance 5% being late for a meeting, I might not care about that too much. But if I think there's 5% chance that if I go on a plane, there's going to be an accident, I'm not going to get on that plane. Right? So 5% means different things in different situations. So there'll be a bit of that, but you see, that's subjective. And you can't get away from that. Now, Fisher, of course, had his subjective. You remember the word convenient, which was 5%. And so now the whole world uses 5%, but that was also subjective. All right. Yes? Okay, so the question is, how do I use it? So the question is, where does the empirical p-value come in? Right here. Okay, so if I have decided that 6% is my cutoff, then for any value of the test statistic that is in this red range, my p-value is going to be less than 6%. Right? So yes, I will put my test statistic down on this distribution. If it is not in the red zone, I'm going to say, yeah, it just looks like a fair coin. If it is in the red zone, I will end up concluding the coin is unfair. The red zone was decided by my cutoff. And formally, the red zone is known as the rejection region. It's where you reject the null hypothesis. Now, there are going to be people in the room who are going to wonder, how did I find this point? Right? So 6% on this side, 94% on the left. Do you agree? That's what we talked about. All right, so it is the what percentile of your statistics? It's the 94th percentile, right? Happily for you, last semester, John De Niro kindly wrote us a little percentile function. Percentile, you give it which percentile you want, and you give it an array of values, and out it pops. That's the 94th percentile right there. 19, that's what you're seeing. Okay? Now, this is not on your exam. I'm just putting it there for the people who really want to know what is that number, right? How do you get the cutoff? And so, if we were doing a 2% cutoff, what would I change here? Remember, this is 2% cutoff. It's 98 because I'm looking at a right-hand tail. And that would have been 23, and I would be cutting off right about here. And the picture, does it agree? Does it not agree? Percentiles are a pain. I'll tell you why they're a pain. They're a pain because your list can have arbitrarily awful size, like 3,187. So then computing 25% of that, you'll get some nasty numbers. Your list can have lots of ties. Things can be equal. So think of a list that has 100 numbers. That's a nice list, 100 numbers, but they're all equal to 72. What's the median? 72. What's the 25th percentile? 72. Yeah, so are 25% of the data below 72? No, 100% are, or 0% are, depending on how you define below. Right? So equality ties are a real pain with percentiles, and we're just not going to worry about them until quite a bit later. It's just there's a formal definition of percentile that I will talk to you about later in the course, and that's what's being used here. All right, so I am going to return to, actually, I'll pause. Questions about anything that's happened thus far? It's not meant to be new. Yes? Oh, thank you.
So 6% the probability, in your opinion, that the coin is unfair?
So 6% in my, okay, assuming that I'm using a 6% cutoff, my subjective opinion is that 6% is a small enough chance that I'm willing to conclude that the coin is unfair. So I have to define what's a small chance. I'm defining 6% to be small. 6% or below to be small.
So your opinion is saying that 6% is probably about the coin?
No. Okay, so let's address this issue. Am I saying that 6% is the probability that the coin is unfair? That 6% is a probability under this histogram, yes? This histogram was computed under what hypothesis? The null hypothesis. If the null hypothesis is true, there is 6% chance of getting a number, If the null hypothesis is true, there is 6% chance that my statistic will be in this range or beyond. That's what the cutoff is. Right? So if you're, I'll come back to this a bit, but the p-value, the cutoff and the p-value, these are both chances that are computed under the null hypothesis. If that chance is small, we conclude alternative. Why? Supposing the p-value came out to be 1%, right? Then if the null were true, there is only about a 1% chance of getting data like the data that we got. In that sense, the data are inconsistent with the null hypothesis. They are unlikely to have been generated by the null. It's a lot to take in. Yes, but why is a small p-value? The question is, why does a small p-value lead us to conclude the alternative? That doesn't have to do with what cutoff you're using. It just has to do with the fact that something inconsistent has happened. Your data are not consistent with what the null predicts. Okay, all of these are excellent questions. This issue is subtle, and one of the things I'll tell you is that based on our experience last fall and last spring, we gave ourselves 2 extra lectures to talk about this. Because it's not just that it's subtle for you, it's subtle for the universe. And I want to show you something, because I'd like you to see what people do. I'm going to show you a statement that came out in a famous journal by a person whom I'm not naming here, but he does have a name. He also has a lab in a well-known university that scores very high on everybody's ranking of what's a great university. Read that. Statistical significance is an objective, unambiguous, universally accepted standard of scientific proof. Here is somebody getting so excited, and what we have just said is statistical significance means that your p-value came out to be less than 5%. If you're using 5% as the cutoff, what's that 5% the chance of? Error. Error. This is a well-known person. This person has a lab in, well, at least at that time he had a lab in a university on the East Coast that people regard as the greatest university in the world. Well, let's take a look at this one by one. Statistical significance, what does that mean? It means something very precise. Statistical significance, any test, means what? You calculated a p-value, and it came out less than 5%. That's what that means. Right? It doesn't matter what the test statistic was. It doesn't matter how you calculated the p-value, left tail, right tail, 2 tails, whatever. You calculated a p-value, it came out less than 5%. Is an objective. Okay, where did the 5% come from? Sir Ronald Fisher. And it came because he thought what? It was convenient. Does that feel objective? It does not. Okay. Unambiguous. That I will give. It's less than 5%, yes. Unambiguous. We understand what it means. It's clearly defined. Universally accepted. Just 10 minutes ago, somebody said, you know what, I'm going to use my definition of what's small, and I will tell you what happens. There's even in teaching here. So the Stat 135 is the first course in sort of mathematical statistics after a calculus-based introduction to probability and so on. In Stat 135, there is a famous textbook that's used all over the world that was written here. And every semester when I teach it, students come up to me and say there's an error in the textbook. Why? Because the author, who is a colleague of ours, says, oh, p-value has come out to be 9%. That seems pretty small. So we are going to conclude on whatever the alternative was, and now we're going to look at more carefully at. Students come to me and say there's an error in the book. What's the error? Oh, he said 9% is small. So I said, yeah, well, he thought 9% was small. But isn't 5% small? Well, Fisher thought 5% was small, but this author thinks 9% is small. Wait, 9% is small? And I have just taken the ground away from the students' feet. Right. I said, well, he thought so. But it's bigger than 5%. Yes, I know it's bigger than 5%, but he thinks it's small. It's a Twilight Zone conversation. You never come out of it. Right. And the difficulty is for a student to accept that people have different opinions, and it's okay. You just have to say what the opinion is. Okay? And it's not just my poor Stat 135 student. Here is universally accepted. Well, the Stat 135 textbook didn't accept it. Standard of scientific proof? No, we've just said 5% is an error probability. This person's a biologist, right? Biology will end up proving. What data science does, it shines a light on where you should look. That is very helpful because there's lots of stuff going on. And if you can identify some principal regions to look at, that's very helpful. Especially when it's science, the proof comes from the science. All right, so let's not get too excited here. Right. So that is the end of my general discussion about testing. What I'd like to do now is we have all of the language, we have all of the methods and so on. I just want to do one sustained example where I'm going to ask you to decide every time, what is it that I'm going to calculate, what are the hypotheses, et cetera, et cetera. Ready for this? Okay, we have 15 minutes, so let's see. All right, football people, Deflategate. The January 2015 AFC Championship game, the Patriots versus the Colts. The Colts said the Patriots' footballs were not as inflated as they ought to be. Why is it useful to have a ball that's slightly not quite as much inflated as it ought to be? Because if the ball is soft, it's a little easier to catch. Right? And so then there was this big brouhaha, and really a big brouhaha. That's CNN right there. Okay, and every expert weighing in on this. The question, did the quarterback was Tom Brady? Did he know? Did he not know? It just went on for days. At the time, you can imagine the fans of the opposing teams were not shy to let their opinions be known. All right, so at the time, there was a lot of discussion. Oh, no, this guy cheats and so on. He's a very fine player. He was suspended, he had to serve, and when did he play after his suspension? Somebody with a hat there. Yesterday was the first time he played after his suspension, and I've just moved on, man. Now, he played very well, very well. He won the game. Anyway, so look, there are balls that are supposed to be inflated to a certain amount. They weren't inflated to a certain amount, to that amount. That's what one side says. The other side says, well, stuff can vary. Okay, fine, data science, we can do this. You ready? All right, we're doing this. Okay, run that. Okay. The data. Now, the body that governs football actually commissioned an independent inquiry by, a firm that does data science. There was a Princeton professor of physics involved who quoted the ideal gas law. All kinds of stuff happened, right? Very, very serious. There are people in other universities still arguing with him about these footballs. Okay, these are the data. There are 11 Patriots balls and 4 Colts balls, and these are 2 people who measured the pressure. The pressure is measured in a standard unit of pressure called pounds per square inch. Higher values means it's more inflated, tighter, more pressure. Okay? All right, please note that there are 11 Patriots balls and 4 Colts balls. I had to read the report to figure out why this discrepancy. First, each team for any game has 12 balls. These were the balls that were used in the AFC Championship game that time. Okay? And what happened was, so each team starts with 12 balls. What happens was that the Colts intercepted a Patriot ball. Right? So an interception is when the other team catches your ball. Right? That's not good. You don't want that. Okay, but they caught the ball and they took it to the sideline and they measured. Right? And they went to the referees and said, underinflated. Underinflated. Okay. That is why one of the Patriots' balls is missing. The Colts have it. Now, where are the other 8 Colts balls? The Patriots did not have 8 interceptions. Where are the other 8 Colts balls? Here's data science. Data science is real. It's about the world. All of this measurement was being done during halftime. Halftime ended. They had to play. So 8 balls never got measured. So these are the data that we have. Right? Based on these data, we want to make some decision. Now, if you just run your eye over, the first thing you note is that there's Cleat Blakeman and Dyrol Priolo. You have 2 measurements on each ball, right? Now what do you do? Well, somehow you need one measurement on each ball, and these gentlemen, well, I just look at them, and this also always seems to be a little lower, but then with this ball, it always seems to be a bit higher. I don't understand, right? I don't understand what's going on with the measurements. I'm a statistician. We just averaged. Yep, which is just an average of Mr. Blakeman and Mr. Priolo. Right now, Cleat Blakeman, this last Super Bowl, Panthers, yes, what do I watch in a football game? Not much, but I watch the coin toss. I watch the coin toss. And, there's a da-da-da-da, the coin toss. It's amazing, right? And who comes out? The referee. Cleet Blickman will toss the coin. I knew the man. It was amazing. I had all his data. All right. This is a serious guy, right? There was not just anybody measuring the pressure. It was the referee. Okay, so we are going to use these data. Now, we are going to compare these 11 numbers to these 4. Yep? Okay, so it just seems apparent that those top 11 numbers seem larger than the bottom 4. But there's an issue raised by both teams and the referees, which is that what's the allowed pressure? The allowed pressure is actually a range. You are allowed to have pressure in the range 12.5 to 13.5. Okay? And it was accepted that the Patriots start out lower than the Colts. So the Patriots start out, it was accepted at 12.5, and the Colts start out at 13. Both are allowed. So if you start out lower, it's not surprising that, with normal, use in the game, that you will also end up lower as well. So you have to account for the fact that the two teams start differently. And so to do that, what I did here, and this will come, the code should not come as a surprise, what I did was I extracted the Patriots balls right here. So how do I do that? Where ball, this is the thing that has the word Patriots in it, so you agree? That seems like a reasonable thing to do? Yep. And then I add a column drop. This 12.5 is what everybody agreed the Patriots ball started at. So we took the drop from 12.5, right? Now, that 12.5 was never measured. That was before the start of the game, right? So nobody was measuring anything then. So the 12.5 and 13 are just something that people agreed on. It's not actually measured data. Play the same game for the Colts, and they have these drops. And now I'm looking at drops of around 1. You agree? And drops of around half. Yeah, and it doesn't look the same to me. However, it doesn't look the same to me is not good enough. I can do a calculation here. Okay, so here's what we're going to do. What I'm going to remind you of is that GSI and the sections. Do you remember? There was a class with 359 students, and there was some 27 people that had a lower mean than everybody. You remember that? How did we end up making that decision? What did we do to the data? How did we generate new sections? We sampled at random from the whole class. Do you remember that? So the null hypothesis was that the section is like a random sample from the whole class, and the alternative hypothesis was that, no, it's too low. Yep? So what we're going to do is we're going to look at all 15 drops. If I just numbers, if I look at these drops, their mean is around 1, this mean is around 1 and a bit and 0.4, and the difference between the means is that. Okay, so what we're going to do is we're just going to look at all 15 drops. We know that the first 11 came from the Patriots, and these last 4 came from the Colts. And we know that the difference between the mean of these first 11 and the mean of these last 4 is 0.73, right? Notice that's positive. That means the first 11 have a higher mean than the last 4, okay? What we're going to say is, well, if the Patriots balls are like a random sample of the 15 balls, then we should be able to just take a random sample of the 15 balls, just take 11 of them, and play this game. Calculate the mean of the 11 that we got and the mean of the other 4, right? Subtract. That give us a statistic, agreed? So what we're going to do is say the null hypothesis is that the Patriots ball is just like a random sample of the 15 footballs of size 11, and our statistic, the alternative is that their drops are too big. The alternative matters. Why does it matter? Being specific about the alternative matters. First, it matters because you're trying to reflect a question that was asked, right, about the data. And this is not just that it's not a random sample, but there's actually too much deflation, right? So the big drop matters, and technically it matters because it affects how you find the p-value. All right? Okay, so what we're going to do is we're going to shuffle these guys, and so, okay, this is a table. We're going to use dot sample. Shuffling, we're going to sample without replacement. With replacement equals false. You remember this from last time? That GSI problem, that's where we used it. Yep. Where's the sample size in there? There's no sample size in there. Default behavior of sample. If you do not produce a sample size, it samples as many times as there are rows in the table. All right? Now, there are 15 rows in my table. It is going to sample at random 15 times without replacement. That is equivalent to shuffling the 15. You agree? Shuffle, pick one, shuffle, pick the next, shuffle, pick the next. You're going to get 15, just getting 15 in a random order. So if I do this, I end up getting that. And, you know, these are the Colts numbers that are kind of mixed in, right? And so if you do it again, you'll get a different shuffle, right? I should actually give you a table that's a deck of cards. Now you can shuffle a deck of cards to your heart's content. All right, take the top 5, that's your poker hand. Take the top 13, that's your bridge hand, et cetera, et cetera. All right, so you agree that we can do this? And now every time I do this, I can take the mean of the first 11 minus the mean of the last 4. Yes? I can take the first 11 by the method take. Yes? You agree that it's taking the first 11? 0 through 10, by now you're all been Pythonized? Excellent. And this is going to go from 11 to num rows is 15, so it's going to get rows 11, 12 up to? Row indexes 11, 12 up to 14. The indices go from 0 to 14. Okay, so this is Python detail right there. Okay, so then this is our new mean of the so-called patriots and the new mean of the so-called Colts, and our simulated statistic comes out to be about 0.5. Our old one was 0.7. Okay? And as you can imagine, we're just going to do this again and again and again and again. Yep? All right, so again and again, we now know how to do this, so we're not going to take terrible amounts of time, except right here. Okay, so our statistic, we start with a blank array. I'm going to do 10,000 repetitions just because I felt like it. Okay, this code is simply repeated. You sample without replacement from drops 15 times, as many times as there are rows. That's a shuffle. You take the first 11 rows of your shuffled and call them the new Patriots rows. You take the mean of that. There's only one column, so it's column 0. You take the mean of that, and that's your new Patriots mean. You take the last 4, column 0, take the mean of that. That's your new Colts mean. Your statistic is the difference between these two. And you append. So at the end of your 10,000 repetitions, you will have an array that is how long? 10,000 long. And each one is a difference of means. Each entry is a difference of means. And your decision is, what do I put in here? I'm going to compute a p-value. Yes? So I have to compare each of these observed statistics, each of these simulated statistics, to my one that I observed. And I'll remind you what I observed here. The one that I observed in the data was right here. So I have a simulated statistic, and I have an observed statistic. How do I find the p-value? So I have to put something in here, right? So it's equal to the observed statistic, or now my choices are the more or less. Yes? So I have to decide, yes.
Well, for the statistic,
Yes.
why did you subtract the mean as opposed to or could you just compare the mean Patriot mean drop to the actual mean drop?
Okay, so I have to compare two means, right? I chose to compare the Patriots means and the Colts means, but you are quite right that you could have compared the Patriots means to the overall mean also, right? So you could have a different statistic, absolutely. I just chose one that was natural. Okay, so now you have to decide, am I looking at the value of my statistic and to the right or to the left? Your move. What comes into play here? The alternative, right? If the alternative is saying that the Patriots' drops are too large, right? What's your statistic? Patriots' drop minus Colts' drop. Yes? If the Patriots' drops are too large, is your statistic going to be big or small? It's going to be big, right? So you're going to look at the right-hand tail of your distribution. The p-value is the chance under the null, you're simulating under the null, randomly permuting, of getting a statistic which was what you got, or more in the direction of the alternative. Direction of the alternative is big values of the statistic, and so this is the only decision that is left to make right there. And then it's all drawing and so on. 10,000 repetitions. Okay, our statistic was 0.733. That is about here. And that sure looks like the danger zone, no matter what you take as your cutoff. Yes? P-value is about half of 1%, right? Okay, so the data say that the balls don't look like a random sample. Important to note, this analysis says nothing about causality. It says nothing about why the data look like this. It just says doesn't look like a random sample. Yes, hands. Okay, that's an NP.A range question. Come down and ask me. We'll sort it out. All right, Wednesday, I'm doing a sort of general review, and I'm going to focus a little bit on probability calculations.